Good morning, everyone, and welcome to today's presentation. I am delighted to have you all here. Today, we will be discussing the calibration of analytical balances, a crucial process in ensuring accuracy in our measurements. The presentation is titled Calibration of Analytical Balance, and it is presented by Dr. S.K. Singh. Over the next few minutes, we will explore the importance of proper calibration, the procedures involved, and best practices to maintain precision. So, let's get started and delve into this essential aspect of laboratory work. Let's start by understanding why calibration is so essential. It ensures that our weighing instruments are accurate and reliable, which directly impacts the validity of all our analytical results. If our balances are off, then everything we measure could be skewed, potentially affecting quality and compliance. In the pharmaceutical industry, the importance of properly calibrated balances is reinforced by the USB General Chapter 41 on balances. This chapter mandates that balances used in quality control labs must be calibrated regularly. It's not just a good practice, it's a requirement to maintain compliance. Additionally, USB 1251 provides guidance on weighing processes and sets performance standards to ensure consistency and accuracy. This helps us understand how to properly perform weighing and what to expect from our equipment. Traceability in calibration is another critical point. It means that our calibration process must be linked to recognized standards, supporting GMP, GLP, data integrity, and audit readiness. Essentially, traceability provides confidence that our measurements are both accurate and defensible. Now, let's clarify some key definitions. Calibration is about establishing the relationship between what our instrument responds and known standards, like traceable weights. Repeatability refers to our balance's ability to produce consistent results under the same conditions. Accuracy measures how close our measurement is to the true value, and measurement uncertainty defines the range within which the true value is expected to lie. All these elements work together to ensure our weighing processes are precise, reliable, and compliant with regulatory standards, which is fundamental to maintaining quality in our work. Let's take a closer look at the calibration framework. This framework is essentially the backbone of ensuring our models are accurate and reliable. It helps us understand how well our predicted probabilities align with the actual outcomes, which is crucial for making trustworthy decisions. When we talk about calibration, we're really focusing on the relationship between what our model predicts and what actually happens in real life. A well-calibrated model means if it predicts a 70% chance of an event, then roughly 70 out of 100 times that event should occur. This consistency is vital, especially in high-stakes areas like healthcare or finance. The framework provides us with tools and methods to evaluate and improve this calibration, ensuring our models don't just perform well in terms of accuracy, but also in terms of the confidence we place in their predictions. Connecting this to our overall theme, effective calibration enhances the trustworthiness and usability of our models. It ensures that the probabilities they generate are meaningful and actionable, which is ultimately what we need for informed decision-making. So, understanding and applying this framework is a key step in developing models that are not only accurate but also dependable. Now, let's talk about the repeatability test, which is a key part of the USB. The procedure is straightforward but important. First, you select a calibrated weight that's approximately 50% of your balance's maximum capacity. Then, you perform 10 consecutive weighings of that same weight, making sure to record each result accurately. The goal here is to assess the consistency of your balance. To do that, we calculate the standard deviation, or sigma, of those 10 readings. The key criterion for repeatability is that 2 times this standard deviation, divided by the nominal weight, should be less than or equal to 0.1%. For example, if you weigh a sample 10 times and get results like 99.995 grams, 100.001 grams, and so on, and the calculated sigma is 0.00015 grams, then you plug that into the formula. So, 2 times sigma divided by 100 grams, multiplied by 100 to get a percentage, results in approximately 0.0003%, which easily passes the criteria. This test helps ensure your balance is reliable and consistent over repeated measurements, which is critical for maintaining accuracy in your overall process. Now let's take a closer look at the accuracy test, which is part of the USB requirements. When performing this test, you'll use a test weight that falls between 5 and 100% of the maximum capacity of the balance. This range ensures we're testing the scale's accuracy across its typical working spectrum. The key acceptance criterion here is that the measured value must be within plus or minus 0.1% of the reference value. To put that into perspective, if your reference weight is, say, 200 grams, then your measured value should be within 0.1% of that, so roughly plus or minus 0.2 grams. For example, if the certificate states that the test weight is 200 grams with a precision of plus or minus 0.005 grams, and your balance reads 200.15 grams, you calculate the deviation by subtracting the reference value from the measured value, which is 0.15 grams. Then, to see if this passes, you divide that deviation by the reference weight, so 0.15 divided by 200 grams, and multiply by 100 to get the percentage. That gives us 0.075%, which is within the acceptable plus or minus 10%. So in this case, the balance passes the accuracy test. This process helps ensure that our balances are precise and reliable for our measurements, maintaining the integrity of our results and compliance with standards. Let's talk about the minimum weight and operating range for the USB balance. The operating range begins where our repeatability is less than or equal to 0.1%, and it extends up to the maximum capacity of the balance. Essentially, this is the range within which we can trust our measurements for consistency and accuracy. A useful way to think about the minimum weight we can reliably measure is through a simplified formula. It's often used in practice. Minimum weight equals 2 times the standard deviation, divided by the maximum acceptable relative uncertainty, which is 0.001 in decimal form for 0.1%. To put this into perspective, let's consider an example. Suppose the repeatability, represented by sigma, is 0.00015 grams. Using the formula, we calculate the minimum weight as 2 times 0.00015 divided by 0.001. That gives us a minimum weight of 0.3 grams. The key takeaway here is that we shouldn't weigh samples smaller than 0.3 grams on this balance, because measurements below that might not be reliable or repeatable. This ensures we maintain accuracy and consistency within the balance's operating range, which is crucial for quality control and precise measurements across our processes. Let's talk about measurement uncertainty, specifically from an USP focus. When we perform calibration, it's crucial to account for uncertainty and traceability. These factors include the reference weight uncertainty, which is how precise our standard weights are, repeatability, meaning how consistent our measurements are over multiple trials, and environmental influences like temperature, humidity, or vibrations that can affect our results. Understanding these factors helps us ensure that our measurements are reliable and accurate. To simplify how we combine these uncertainties, we often use the basic uncertainty combination formula, which looks like the square root of the sum of the squares of individual uncertainties. So, U total is approximately equal to the square root of U weights squared plus U repeats squared, and so on for other factors. For example, if our reference weight uncertainty is 0.1 grams and repeatability is 0.05 grams, we can calculate the combined uncertainty to get a more comprehensive picture of our measurement confidence. This approach helps us understand the overall uncertainty in our calibration process, reinforcing the importance of traceability and precision in quality control. This concept ties directly into our overall goal of maintaining high standards and ensuring our measurements are trustworthy. Let's continue our discussion on measurement uncertainty. As we explore this topic further, I want to emphasize that understanding the uncertainties involved in measurements is crucial for ensuring accurate and reliable results. In this slide, we'll focus on some key points that build on what we've previously covered. First, it's important to recognize that measurement uncertainty isn't just about errors, but about quantifying the doubt that exists in our measurements. This helps us understand the confidence level we can have in our data. Next, we'll look at different sources of uncertainty, which can be random or systematic. Random uncertainties tend to fluctuate and can often be reduced through repeated measurements, while systematic uncertainties are consistent biases that need to be identified and corrected. Recognizing these sources allows us to better control and account for them in our analysis. Finally, connecting this to our overall theme, appreciating and properly managing measurement uncertainty is essential for maintaining integrity in our scientific or engineering work. It ensures that decisions based on data are informed by a clear understanding of their limitations, ultimately leading to more robust and trustworthy outcomes. Now, let's look at some practical calculations using an analytical balance. We start with the given data. The balance's readability is 0.1 milligrams, which is equivalent to 0.0001 grams. We're measuring a test weight of 100 grams, and from repeatability tests, we have a standard deviation, sigma, of 0.00015 grams. Additionally, there's an uncertainty associated with the calibration certificate of the reference weight, which is 0.0002 grams. These figures are crucial because they help us understand the measurement's overall uncertainty. The balance's readability indicates the smallest increment it can reliably detect, while the standard deviation tells us how consistent our measurements are when we repeat the test under the same conditions. The calibration certificate uncertainty adds another layer, reflecting the possible error in the reference weight itself. All these factors combined influence the total measurement uncertainty, which we need to evaluate carefully to ensure our results are accurate and reliable. By thoroughly analyzing these components, we can better understand the precision and confidence level associated with our measurements, which is essential in quality control and compliance processes. Now, let's take a look at the final reported result. We have a measurement of 100 grams, with an uncertainty of plus or minus 0.0005 grams, using a coverage factor of 2. This essentially means that the true value is very likely to fall within this range. Specifically, we can say with about 95% confidence that the true value lies somewhere between 99.9995 grams and 100.0005 grams. This range is crucial because it gives us an idea of the precision and reliability of our measurement. When we talk about measurement uncertainty, we're acknowledging the inherent limitations in any measurement process. And as we've seen, understanding and properly reporting this uncertainty helps us communicate our results more accurately and confidently. So, in the context of our presentation, this highlights the importance of not just the measured value itself, but also the confidence we have in that value, which ultimately supports the overall integrity of our measurement process. Let's talk about documentation and records, which are vital for maintaining calibration integrity. When you record calibration activities, make sure to include the date and time, along with the specific equipment ID. This helps us track exactly when and which equipment was calibrated. It's also important to note the environmental conditions during calibration, like temperature and humidity, since these can affect the results. Recording the weights used, including their class and certificates, ensures traceability and accuracy. Be sure to document the as-found and as-left values, so we know the equipment's state before and after calibration. Record the repeatability and accuracy results to demonstrate the consistency and reliability of the calibration process. Including an uncertainty evaluation is crucial, as it provides an estimate of the potential error in our measurements. And finally, all records should be signed and traceable, ensuring accountability and proper documentation for audits. Speaking of audits, remember that calibration certificates need to be retained properly, as they serve as official proof of compliance and calibration history. This thorough documentation supports both quality assurance and regulatory requirements, tying into our overall goal of maintaining reliable, accurate measurement systems. Let's talk about risk-based calibration frequency. USB emphasizes the importance of setting calibration intervals based on scientific justification rather than sticking to arbitrary dates. This means we should consider several key factors. First, how often the equipment is used. More frequent use might require more regular calibration. Second, the criticality of the measurements. If the measurements are vital for product quality or safety, it's worth calibrating more often. And third, the performance history of the equipment. If it tends to drift or shows signs of inconsistency, that's a strong reason to adjust calibration intervals accordingly. An example schedule might include daily internal checks to ensure everything is functioning properly, along with quarterly full calibrations. Of course, these intervals can also be adjusted based on a thorough risk analysis. The main idea here is to tailor calibration frequency to the actual risks involved, ensuring reliability while avoiding unnecessary calibrations. This approach aligns perfectly with our overall goal of maintaining high quality and compliance through scientifically justified practices. Let's talk about some common errors we see when it comes to operating or calibrating analytical balances. First, using weights with poor certification is a big mistake. If the weights aren't properly certified, it can lead to inaccurate measurements, which affects the reliability of your results. Next, ignoring environmental stability is another common issue. Factors like drafts, vibrations, or temperature fluctuations can all impact the balance's performance. It's essential to control these environmental conditions to ensure accurate readings. Then we have forgetting to tare the balance or handling samples incorrectly. Tarring is crucial because it zeroes out the container weight, and neglecting this step can skew your results. Also, improper handling, like touching the balance pan or the sample, can transfer oils or moisture, leading to errors. Finally, there's over-reliance on old minimum weight values. Sometimes, users rely on outdated calibration data or minimum weight thresholds that no longer apply, which can compromise measurement accuracy. All these errors highlight the importance of proper procedures and attention to detail in maintaining the accuracy of your analytical balances. Staying vigilant about these points helps ensure reliable and valid results in your work. Let's take a closer look at this case study involving an analytical balance with a 220-gram capacity. Here, we've performed some key tests to evaluate its performance. First, we measured the repeatability, which is how consistent the readings are when we measure the same sample multiple times. In this case, the standard deviation, sigma, was 0.00018 grams, a very low value, indicating excellent repeatability. Next, we checked the accuracy by using a 100-gram weight and comparing the balance's reading to the actual weight. The deviation was 0.085%, which is quite acceptable for most applications, but it's important to see how these figures align with industry standards. Now, on the table, you'll see the specific tests, the results we obtained, whether they passed or failed based on our criteria, and the relevant calculations. This detailed breakdown helps us understand whether the balance performs reliably under different conditions. The key takeaway here is that both repeatability and accuracy are critical for ensuring trustworthy measurements. In this case, the balance shows strong performance, but always remember, continuous testing and proper calibration are essential to maintain measurement quality over time. This case study exemplifies how we evaluate equipment to ensure it meets the required standards for precise and accurate measurements in our processes. All right, let's wrap up with some key takeaways. First, calibration is absolutely mandatory, as outlined in USP 41 and 1251. It's not optional, it's a regulatory requirement that we all need to adhere to. Next, we must ensure that our balances are fit for purpose. That means demonstrating both repeatability and accuracy, that they consistently give reliable results and are precise enough for our needs. It's also crucial to include uncertainty and traceability in our calibration processes. Understanding the margin of error and being able to trace measurements back to standard references helps ensure the integrity of our data. Using a risk-based frequency for calibration is another important point. This means calibrating more frequently when the risk of measurement error is higher, and less often when the risk is lower, optimizing resources without compromising quality. And finally, strong documentation is vital for compliance. Keeping thorough records not only proves that we're following the regulations, but also supports ongoing quality assurance. So, to sum up, consistent calibration that's properly documented, risk-based, and technically sound is key to maintaining quality and compliance across our operations. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. And with that, I want to sincerely thank you for your time and attention today. It's been a pleasure sharing this information with you, and I hope you found it valuable. Remember, we're always available to assist you as you move forward with implementing these ideas or strategies. Thank you once again, and have a great day.